Today I'm going to talk about image classification on marketplace data. Schibsted actually recently split into two companies. There's the media and the marketplaces. So I'm in the marketplaces, Schibsted Marketplaces. And yeah, that's the focus today. What particularly I'm going to go into is this sort of choice that's emerged between doing fine-tuning and prompting. We've been trying out both of those approaches recently in different settings, but in this case on classification. So this is what we're going to talk about. Yeah, just what those approaches are. Then a little bit about just how one does classification with prompts. Then a little bit about training this clip model as an alternative approach. And then focusing on the problem at hand, which is classification into the Tori taxonomy. Tori being one of the marketplaces at Schibsted Marketplaces. Yeah, and then the results that I'll present, I'll yeah, speak about prompting and fine-tuning results. So yeah, if we just sort of take a historical perspective, as we all know, if we really need to set the context, we need to go way back to the Gracchan reforms and then on to the fall of the Roman Republic. But then moving on. So is that a question? Or
yeah, yeah.
I can't see you guys at all, by the way.
No, you were sharing your screen before, but then I think you took it down, and I said it was fine. But I was
okay. Oh, my bad. Sorry.
Mine as well.
There we go.
There we go.
That's oh, good. Okay, there we go. Right, here's my nice slide with the history. And yeah, but basically, what happened in 2012, right, was AlexNet paper came along, and this just opened up all sorts of possibilities where people could actually get great results out of deep learning models, and that sort of led to a whole bunch of different efforts of fine-tuning models, so doing transfer learning on top of deep neural networks for image classification, and then not too long after that, there was the GPT-3 paper on using these machine learning models in a very different way, but still getting this sort of adaptability out of them by doing few shot or even zero shot prompting. Today, at least I've felt working on different problems that we're often presented with a choice between those two approaches, and it's not necessarily obvious how to proceed. So yeah, we've been trying out different approaches. But just focusing on the prompts themselves, as we all would have experienced, that there is pretty incredible things that you can do with prompts. And this slide is a year old now, but even then it was clearly astounding what you could do, generating images and all sorts of text applications, and even generating video, let alone text to speech and so forth. But then one of the things you can do with it is the relatively mundane task of classification. How does one actually do classification with prompts? I mean, there are various different ways to do it, as we'll explore shortly. But one of the most just obvious ways to do it is you just construct your prompt and you specify the different output categories that you're trying to classify into, and then you get your output and you just parse that, and yeah, you can make a decision like that. So you can do it in a very basic way, but we'll explore another technique a little bit later on. But yeah, if you just doing classification with prompts, it's extremely convenient. Several advantages. One is just the convenience. You just make a simple API call to a large language model or a vision language model. And with the frontier models like Claude and the OpenAI's models, you often get really great results just out of the box. But there are some drawbacks with those with that technique. So you have no access to intermediate model outputs, and you also have quite high latency potentially. Now, the first of those points, I would hazard a guess, at least with these proprietary models like GPT-4o and whatnot, that's probably going to continue to be the case. So what I mean by that, intermediate model outputs, so as we know with one of these like transformer models, you feed in your input, and then there's these layers where they sort of output, after each layer, there'll be like activations from the model that you can actually look at potentially. But in the case of these models, you can't look at those. And not only you cannot look at those, but you can't use other tricks such as computing gradients and things. And so various sorts of other things that you'd be able to do in an open model are just not available. Like there's various sorts of interpretability things that you can do otherwise. And also just getting the probabilities of the output tokens is something that is not available for some of these APIs at least. And also the latency issue, that is often not really a concern, right? But in some cases, in our case in particular, it is a bit of an issue. So it can be several seconds, especially if you're inputting image data in particular, because that adds up to a large number of tokens. I think that's the reason why it takes long if you use like GPT-4o. And bear in mind though that it's probably I would predict that's going to improve. There's all sorts of developments in this field, and someone will come up with some trick. So this waiting time for API calls for running like GPT-4o with image inputs, I would not necessarily expect that to still be a problem in, say, a year's time, but it is a problem right now, and that's what we got to work with. So there are other approaches. The traditional approach, let's call it, would be to do transfer learning with a deep neural network in just the most standard way. If you're talking about image classification now, so in this setting, you have a pre-trained image classifier. So it could be some model like a vision transformer or a ResNext model, were two of the ones that we've tried out, that model has been pre-trained on a task like classification into the ImageNet, according to the ImageNet data set. And then what you do is you just sort of chop off the final layer of that network and then replace it with a new layer that's going to predict N output categories. And then you fine-tune the weights of that resulting modified model on your data set that has N output categories with this cross-entropy loss. That's the standard sort of most common approach. A more recent approach is using this model called CLIP, which we're going to talk a little bit about today. So it's this contrastive language image pre-training. Spelled language wrong there. Whoops. So contrastive in the sense of contrasting. I think this is why it's called a contrastive loss. It's like contrasting, like this should be a better match than these other matches, basically. But how the pre-training works there is quite different to the approach I just mentioned a moment ago. So here, under the hood in a CLIP model, you've got a text encoder and an image encoder. And so there's actually two models sort of being used in it. And what you do is you feed your text in. So here an example is Pepper the Aussie pup, goes into the text encoder. And you also have your image. So in this case, a dog that obviously is semantically a good match to this text in this case. And you get an embedding for the text encoder and from the image encoder. And you can do this for a batch of images and a corresponding batch of texts. So that's what this figure shows here. So each of these is supposed to be like the embedding for the ICE image here, and this is the embedding for the ICE text here. And then you can compute your similarities between pairwise between each of the possible pairings there, and the loss is based on that. So basically, what the loss computes is that you should have high scores, high similarities for this diagonal here, where the images match. So these paired ones, and low scores otherwise, and that's what the loss sort of calculates. And then once you've got your clip model pre-trained, you can actually do classification with that. So that this is just the following paper figure from the clip paper itself, where they explain this approach. Yeah, basically how that works is you create a data set of texts. So you've got your different categories that you want to classify into, and then you generate for each of those categories a text. So that could be, for example, a photo of a blur, like a plane or a car, a dog, whatnot. And then you feed each of those texts into the text encoder. And so you get these, you've got n different classes, you get your n text embeddings, and then you take your given image that you're trying to classify into these different categories into your image encoder, you get your embedding, and then you compute the similarity of it against each of the text embeddings. And the one that you're going to pick is the one with the highest similarity score. And what you can also do is fine-tune clip. So in this case, we're doing classification in a zero-shot way. So we haven't trained it on our particular data. We've just fed in the classes that we want to classify into, and off we go. But what you can instead do is you can feed in your own data into additional training. So this is, I've adapted the figure they had for explaining the clip pre-training here. And yeah, what you do is you've got your own data set. So that could be just, you just have to provide like text image pairs. Yeah, you can actually train clip further to get better results on your particular data set. So yes, that brings us to our task, which is classification in this Tori marketplace, Recommerce marketplace. So Tori is Schibsted's Recommerce marketplace in Finland, and users create ads for this marketplace via web or iOS or Android interfaces, and we want to improve the ad creation process in various different ways, and automated classification is part of this. Yeah, what are these categories? So this is just a little screenshot of part of the interface in the web, the website for Tori, showing these top level 1 categories, and actually the English translations here. And yeah, the taxonomy, it has 3 levels and 600 nodes, 521 at the leaf node level. And most of those are 3 levels down, but some of the leaf nodes are actually at level 2. Like, for example, antiques and art, antique furniture is that doesn't have any child categories, whereas here we've got like down here, antiques and art has various child categories such as acrylic paintings. So let's talk about some what we actually did and some results. Before we go into the Tori results, I want to go on a little bit of a tangent and talk about yet another approach to classification, which is again a prompting-based approach where you don't have to do any training. You're just making API calls, but in this case, you're using these logprobs from OpenAI, and I'll explain why that's useful. So a little bit of just taking a step back, large language models and vision language models, at least when you're generating a text token outputs, so they're classifiers in the sense that what you're doing is a classification call each time you're generating a token. So this slide is a bit old, so it's GPT-4 here, but if you have your input text and then you're trying to generate the next token, you're choosing between the different alternatives, and you get a probability for each possible output token. And nowadays, of course, we have multimodal models like GPT-4o from OpenAI, but when you're generating text, you're getting probabilities, and this is very useful actually for various reasons. So each token output is a classification call, and so then if we actually just use a suitable prompt and we're just retrieving output probabilities for our classes of interest, then we've got our classifier that doesn't just classify into these output classes and just that's it. We can also get a score back, which is obviously useful for different reasons. Why would we use this? So just classification tasks, but also, there's other reasons as well. Like if you're trying to sort of build system with AI agents or something, maybe it's useful to actually be able to get a score back and then set a threshold or whatnot, and thereby tune the trade-off between precision and recall or whatnot, without having to somehow achieve that result by just modifying the text prompt that you're feeding in. And this is a recommended approach by various experts, including, by the way, I heard a podcast with the person at AI who's she's leading the team doing this structured outputs stuff, and she said that this is the way to go with classification. If you want to get a rating on something, what you do is you pose it as a classification task and then get the logprobs. Great. How does it actually work? Well, you specify that as one of the arguments when you make your API call to the chat completion endpoint, and you can get up to 20 of them. Unfortunately, you can't get all of the probability log probability values for the entire vocabulary. That would be nice, but still it's something. And as I alluded to before, not the case for all of the different models as far as I could tell. I don't think Claude offers you that, for example. So let's look at an example of how this would work. Car damage rating, which is just an experiment that we tried out, sort of proof of principle. So in mobility, as in marketplaces where they're selling cars and stuff like that, it could be useful to detect when there is damage to a vehicle for sale. So what I did was use GPT-4o to score a bunch of car ads from Finn. That's the Norwegian marketplace that includes cars as well. Scan them for whether there's any damage to the vehicle and ranked on this score, and look at the top and bottom ranked ads. So this was the actual sort of bit of code making that API call, and we're just specifying our prompt, and I'm just posing it as just a yes or no thing. Is this car in pristine condition without any blemishes whatsoever? Just answer yes or no. And then here, when I actually make the API call, I'm just specifying I want a single token back, and I'm asking for the logprobs and up to 20 of them, and then I'm just getting a score for yes or no if there exists, otherwise giving them a low value. Then if we look at the outputs for the scores for those for the various tokens were actually retrieved for a given ad. So this was the top ranked ad in terms of the yes or no, yes minus no scores. Yeah, we can see that well, these are the actual scores. So and if we look at this one, not so much the case. No actually is the highest scoring one, and it really doesn't have yes. Well, yes is down there, but most of the tokens it's trying to say no somehow. 9, and yeah, it's as you can see, it is indeed not in great condition. So just an illustration that you can actually then rank something on that rather than just getting yes or no, and then you're sort of lost with in terms of being able to actually get quantify the result. Okay, so let's look at another interesting example, Recommerce attribute prediction. So this is again focusing on the Fin taxonomy. So not Tori, we'll get to that in a moment, but yeah, these the categories often have specific attributes. So if we're looking at the washing machine category, we have the brand and type attributes, and it would be nice to be able to predict those attributes. So yeah, retrieved a bunch of ads and created a validation data set to assess how well this approach works, and applied it to brand and type. So we look at brand here. This is like the formulation of that classification. So it's not just yes or no, right? We've got different possible brands that we want to classify into. And so what we do is we just assign a unique symbol to each of the possible brands. And you need it. What you need here, though, from my thinking about it, is you need just a single token to correspond to each of these like symbols that you're using, denoting the different categories, which still feels like a bit of a hack, but anyway, that you need each one. You need individual tokens because you're retrieving the log probability for individual tokens. So yeah, then this is an example of that actually working in practice, where it pulls out that this is a Bosch washing machine. And if we look at type, there's less possible categories there, just the front loader, combined wash dry, compact, top loader, or other. And it's able to do that reasonably well. Yeah, but there's a problem, and that is as I mentioned, we're sort of relying on having a single token identifier for each of the classes that we then put in front of the classes when we're listing them all. And there are lots of classes, so 521 leaf node classes with the Tori leaf nodes. So I've tried it out, this logprob approach, by trying to sort of choose a particular, a suitable sort of Unicode like place in the, like enumerating over those but I felt it didn't really work so well. And so I'm curious about how to really make this this sort of logprob approach, which again feels like a bit of a hack but works, like how this approach should work with many classes. And I'm curious actually if any of you tried anything like this or come across this sort of issue. But anyhow, it's a problem. And so for this particular case of the Tori taxonomy classification task, I've actually just gone back to just specifying, just give me the top 5 best categories and just print them out, and then I just split them on the lines and match them back, and that's how I do the classification. So I don't get the probabilities, unfortunately, in this case. But yeah, the results of that approach, just the prompt and ask for the outputs, and then off you go, get the top 5 predictions, is as follows. On a validation data set from Tori data, with where the data set here is paired images and categories, so where the category has been selected by user generating the ad. So we get actually pretty decent performance, I would say. That if it's allowed to make if you just take the top prediction, so you just take the very top one there, in sports and outdoor activities, ice hockey and skating, skates for women and men, in this example, then just over 60% of the time, that is correct. If you allow it to take the top 3 predictions, then it's correct about 79% of the time, and top 5 is like almost 85% of the time. But there is another problem, and that is that it's slow. It takes several seconds, and we did not like this. And so we've tried some other approaches. And in particular, what we found has worked quite well was fine-tuning clip on Tori examples. So the data set we're using to fine-tune clip is, here's an example. Like you've got your image from the ad, and then you've got some text that denotes that category that was actually selected. So car, boat, and motorcycle accessories, car parts, roof racks, and ski boxes was the selected example in this case. And you've just got a whole bunch of those pairings, and you do that clip training as I described before. So this is these are the plots from TensorBoard from that training. Yeah, we observed that with our validation metric here, it improved up until the end of the second epoch. We're dropping the learning rate here after each epoch, and then it sort of started to go down, which sort of indicates that it's overfitting on the data at that point. But there was an interesting thing I just wanted to highlight here with the loss function on the training data on consecutive batches from the training data. It really jumps up and down. So if you take the sort of broad perspective, it does gradually go down. But if you're just looking initially, it's like jumping all over the place. And I tried a few different things here with normally when it's sort of jumping up and down like that, with at least with like a task such as just image classification with like the standard transfer learning approach, or like fine-tuning an LLM on some data or whatnot. I just anecdotally, I seem to recall that it's easier to get it to just smoothly go down. But my impression from this clip training is that it's sort of a bit jumpier, like that just how that loss function works with batches. It's more stochastic, and it's I tried to reduce that problem by increasing the batch size as much as I possibly could. But that was just a curious, albeit totally anecdotal observation. But yeah, training worked. The loss went down, and the validation accuracy improved, top 3 accuracy. And we got better results than with GPT-4o. So we achieved a top 3 accuracy, that's the key one, of almost 2%, around 2% better. Yeah, it's pretty nice. But if we look at where it goes wrong, that's sort of interesting. So, it does struggle for certain categories. So here, this column shows, like, given that the example is from a certain category, so in this case, say like entertainment and hobbies, food, like what fraction of the time on such input images will that category be in the top 3, and it's just abysmal at certain categories. But bear in mind this is just the top of a list of like 500, so it's actually good for the vast majority of them. But it's still interesting to look at why it fails for these. One thing we note is actually almost all of these are top 2, level 2 categories, not level 3. And actually, I didn't mention it a moment ago, but I mentioned it now. The training that we've done was actually only on level 3 categories from the Tori data set. One examples where the leaf node is level 2, and that's the one that the user has selected. We've not trained on those, but nevertheless, the model is able to make predictions for those because of this this clip setup, where you can feed in any text that you like to the clip text encoder. So in this case, we've fed in entertainment and hobbies food as one of the text to the text encoder when we actually want to make predictions, even though that was not fed in during training, which is a nice aspect of using clip. And it does actually make predictions that are better than random. So we'll dive into that in a bit. But I mean, the point here, selecting this example, is that this is the only example where it's a level 3 category from these worst ones. So it does seem as though that's probably got a lot to do with it, that it wasn't specifically trained on those. So yeah, but nevertheless, looking at one of these examples, so children's and parents' maternity wear, that the errors do seem totally reasonable. Like it's trying to classify it into these presumably very reasonable alternative categories. This is the fraction of the time that an example where the user has specified that was classified into the given category here. And performance is far better than random. If we just look at predicting that category versus everything else, and then do an ROC analysis, then it's far better than the random guess. So yeah, getting to the end here, but there was just one other aspect that I wanted to present that was sort of interesting, I thought, and quite useful. So with the clip approach, or if we had been able to, find a way to classify well into the 521 leaf node categories and get probability values using GPT-4o, but we didn't. So just with the clip approach, we can get probabilities back, right? And that's useful because we can threshold on those. So hang on, sorry, my light just went out in the room. There we go. Yeah, so what we can do is, well, what I've done in this case is just take the top 3 predicted categories and just sum up their probabilities, and then apply a threshold on that. And then if the sum is greater than that threshold, then we would actually show those predictions. Otherwise, we would just not show those predictions. So in the setting of actually using this in the app, you would then, the idea is that you would only be shown these automated predictions if the probabilities are over a certain value. And yeah, this actually this analysis shows, like, basically if you set a threshold of like 90%, like those top 3 adding up to 0.9 or higher, then you can actually get those predictions being correct more than 80% of the time. This is actually on a previous version of the model, so it was actually not as good as that 80% figure that I showed a moment ago. But yeah, basically you can use these probabilities and threshold and thereby get the accuracy level that you want to achieve, even if the classifier doesn't produce that level of accuracy by default. Yeah, So in conclusion, this the fine-tuned clip model does outperform GPT-4o prompt, at least with what we've tried, and is faster, crucially, and also enables probability thresholds. But yeah, it's quite a bit of work to do this. So it's a trade-off, and yeah, we could maybe go to questions now. I'll just stop presenting. Yeah, go ahead, Olivia.
Hi, thank you for the presentation. I have a question regarding the tokens that you mentioned, that you were using like 26 tokens of the alphabets, but I understand there are many more tokens in GPT-4o, tens of thousands.
Yep.
And also I wonder, I mean, you have a tree structure, right?
Mm-hmm.
You're trying to classify according to a tree structure. So
That is
actually you would need to, you could use, I don't know, but I guess you could use the first level.
Yep.
Maybe you have 10 at the first level, so you use 10 tokens, and
Yep.
then you the second token to give you the second level. You could do, maybe you could do that. I don't know if you something that.
Yeah, I was similar
it's right.
thought. But to your first question, yes, indeed, there are tens of thousands of tokens that it has, and I tried that. I tried specifying like a range of tokens in Unicode. I just sort of didn't like go back to Anyway, yeah, I tried that approach basically to just sort of have a separate token, but the tokens were super obscure that I ended up getting like some weird character. Anyway, I assessed performance on a data set, and it just was far worse than I was getting. So I tried it out. The second approach that you mentioned, though, I have not tried that yet, and I think it's a good suggestion. The trouble is, though, from what I'm thinking about, if I understand it correctly, is that it's already slow, right, to make just a prediction. So if I need to make level 1 prediction and then get the result, and then you go down to level 2 and then level 3, it's like just too slow. So maybe there's some clever way around that, but yeah, these are the kind of techniques that one could use. But yeah.
Thank you.
Thank you. I'm curious if you folks have been trying out actually any sort of classification tasks with these models, with API calls to like OpenAI or Claude or Gemini or anything, or even local models, or yeah, it's a super handy trick, right? I mean, in the way I think about it is just in the everyday world, we're going around making decisions all the time, and we're trying to sort of create systems that can sort of emulate how humans deal with different tasks. Then you need to build pipelines that consist of lots of individual decisions. So you really want to get good at making, like, just spinning up a little classifier to make one of those decisions, and to do it well, and to be able to make that classifier easily. So yeah, generally I would sort of go for just an API call, I think, because it's so convenient. But yeah, Tab.
Yeah, thanks for the talk. This clip is I'm just loving. I love what I hear, and especially like I guess I'm imagining kind of like the different data types, like comparing, like encoding, embedding them, and then comparing, the outputs there. I love that application, and I wondered, have you seen that even outside image classification, other types of classification, or any other models that being applied to?
Yeah, that's an interesting thought. So if I understand right, like you're thinking like other modalities besize, like if you fed in like
comparing, different modalities, basically.
I've only seen clip like that's a good question. I hadn't thought of that. not in that exact setting, but like this contrastive loss, I feel a little bit sort of insecure about this because I'm not really sure about this, but
okay.
I don't know that's quite a commonly used technique though, the contrastive loss thing. This idea that I think the idea is there. You've got this, you've got like a batch of data, and like you've got these possible pairings, and you've got like that like this pairing of like in this case image to text. This particular pair is like a correct pair, and this other pairing is an incorrect pair, and you could do that with lots of different sort of inputs, and people do like that for sure. Is like this contrastive loss thingy is become quite ubiquitous in the field as far as I understand, and but more directly though, to answer your question about like how it is with like. Maybe you could feed in like sound data or something.
Yeah.
I haven't seen that. I'm not even sure how that would look actually. I don't know how people like, nowadays.
Could like, the sound of a motor be like, oh yeah, this is the picture of that motor. I don't know.
Yeah, totally. I mean, like you could do that in principle. I have to look out for that. Yeah.
All right. Yeah, no, well, thanks for keying me onto it. Yeah, no.
Ooh, there's so many of you. It's Was there
another question from Olivier or?
Yeah. I was just you mentioned briefly the open source models in the beginning, I think.
Yes.
Because then you have more access to maybe the last layer, and so you can do whatever you like, basically. Is it something that you tried? I guess the downside is that it's going to be even slower because you'd have to have a very, very fast machine. I don't know.
Yes.
Why? I mean, did you try any of those?
We've tried them out in different settings. In other projects. So as I mentioned, the Schibsted split into media marketplaces, and I'm working on marketplaces. But before that split, I was doing a bit of work in media stuff. And we were using it to trying small models out for generating like titles, like fine tuning on article titles, and my colleagues got some very nice results on that, and tried it out a bit as well. And it's one thing, there's a few things worth mentioning there. I mean, another possible advantage, we're talking about the LLMs there, like similar to here, is you can actually just get flat out better performance than like GPT-4, GPT-4o or whatnot, if in certain cases, and it sort of depends on the case. Like another one I keep hearing, or maybe it's maybe like a year ago I keep hearing about, was like SQL code generation, where if you fine-tuned a small model to generate SQL code, you get just straight out much better results than if you were using like prompting GPT-4 back then. But then also, that's not really what you're mentioning though. It's like the interpretability thing. And yeah, there are some fun things that you can do there. Like what you can do is this, like these gradient-based techniques for getting insight into what the model is doing. So if I can remember this correctly, you are like at a given level in the transformer sort of output, you can get the activations from that, the output activations for each token, and then you basically want to ask the question like, how much would it change this final output token's probability if I were to change this input token just a little bit? Like if I were to mess with that input token, what would that how much would that change the if I mess with the input token, how much would that change the output token? And you can do that for all of the input tokens. And like that's what you do if you compute the gradient of those output, the input, those intermediate activations for the input tokens with respect to like a given output probability for a certain output token. That was a bit of a convoluted You sort of need a slide.
No, I understand perfectly. I worked on that also, so I
Oh,
totally
oh,
understand.
really? Oh, cool.
Yeah.
Yeah,
It's
I
very
really,
hard to do any of this interpretation, in my opinion. But I was thinking at least you can have access to the next to last level,
Yes.
and then your token problem disappears because you know exactly how many there are and so on. I don't know. I was just wondering if you have used these open source models at all, or if it's not an
Yes,
option.
we have.
Some people say that these commercial models are so much better than there's no use for these open source models. I'm
Yeah.
thinking about the ones that Mistral or or Facebook releases, these llama models that you can run on your own computers. I was wondering if you're using them sometimes, or if it's completely ruled out.
Yeah, no, it's not ruled out at all. I think it's important to not rule out this. This field is moving so quickly. I mean, just look at these Quen models that have come out just in the last, days, as far as I understand. Very recently, like there was this Quen Coder model, and then there's this other 32 billion parameter Quen model with very permissive license as well for commercial use. And they're doing great. Like there's this new reasoning model that's like a competitor to like the O1 preview model that is like getting very, by some benchmarks, very good results. So I'm very curious to try to see how that goes. So for those sort of like, there's this ongoing competition between the open source models and the closed proprietary models. And so it's important to just not rule out this, and just, choose one. And I feel just because then you might not get the best, maybe in 6 months' time, the best results are from open source models. And then you want to be able to, you don't want to sort of rule that out. And so I feel like it's important for us, at least, as an organization, to keep engaged with trying these models out here and there, and in some cases it'll be the way to go. But yeah, it is. Having said that, I have mixed feelings about it because it is a lot of work to like. I'm not really sure about we got better results here. We clip it. It fit the bill. It's faster. That crucially it does address that latency concern, but it did take a lot of work to get that. Right. It's a tricky decision. Hence the meme with the guy with the buttons, like fun.
Yeah.
So, yeah.
I see. Thank you.
Thanks. Yeah, maybe I can comment a bit on some things that both of you said, Thomas and Olivier. So, Tom, you asked if anyone else had done this classification by prompting, and we did try that a bit in a project about content moderation for an app for teenagers. I mean, there are several aspects here. Like one of them being we weren't allowed to use OpenAI or Anthropic or something like that because of privacy concerns.
Yes, that's the other big one, right? Yeah.
And it's often like that for many of our other projects as well. Right now, we're working with the document interpretation case where we also can't use any cloud models. We have to use local models. But anyway, in that one, in the kids app, we were only able to use fake. So we used the Claude a lot actually to make fake examples that we could then try these different classification strategies with. And it worked. It worked pretty well, but it worked about as well as our old fine-tuned BERT models. And of course, the latency was higher, and it cost actually a fair bit of money as well. So, and we couldn't use OpenAI or Anthropic, and we did try Llama and Mistral, but they were really much worse. It was in Swedish. So I think Llama and Mistral are not good at Swedish, at least not at the time.
But that was the classification task then, or that?
Yeah, classification for like, should this message be moderated or
Yeah.
not?
Right. Yeah, but I suppose that in another setting, if it had been like slightly different, like you still had that sort of strict privacy constraint thing, you're not allowed to use OpenAI, blah, blah, blah. But if you're generating text output, then maybe it would, yeah, there's like a niche there. I'm just waiting for that opportunity to emerge where my hands are tied. I have to use local model. Sorry, nothing I can do.
Yeah, no, I'm also really interested in these Quen models actually.
Yes, they're very cool.
They have a vision model as well that has come out recently that is supposed to be great, 70 billion parameters.
Yeah.
Which
There's also this Olmo, something about some Olmo model I keep sort of floating around. I don't know who did that. I just had
I don't know.
Oh yeah. I just want to do a shout out to Natalia there. I just noticed you on the call. We should work together at Schibsted a couple of years ago. Yeah, hello.
Yeah. Hey, great to be here and listen to you talk. It's many new ideas.
Yeah.
We work together. It's really, really great to hear.
Yes.
I had a question as well about the clip fine-tuning. Like, how hard is it to do? Do they have a nice way to do it, or do you have to go in and hack the code yourself? Or...
there are a couple of interesting things to reflect on there. Yeah, it was pretty nice. I mean, it was not like it was just some PyTorch code. We in hindsight probably ought to have used like PyTorch Lightning or something to make it a bit cleaner, but we just had this PyTorch code, this loop, and this evaluation, and it worked. It was one thing that's interesting with these clip models again is that you've got the image and the text inputs. So and when it comes to actually running it, what I was initially doing was just running the model, the forward pass in the model, just black box, just like here's the inputs, text and image, all the different classes, and run it. But that's really, you don't want to do that in this case, because the thing is that's very slow when you're feeding in all of the text classes, and unnecessarily slow because you only need to do that once. Like when we're actually putting this into this app that Python app for actually doing this, we're running the PyTorch code. What you want to do is you want to run the text encoder on all of the possible classes, the text representation of those classes. Once when you start the app up, or maybe in advance and you store the embeddings or whatever, but you don't want to do it each time you get an image coming in. Because it's super slow there, and that really mattered. But initially, if you're just sort of just going, I will just run the model, so I'll just do a forward pass and just call model inputs, then that you get bad results there, and that's why. So in terms of going to your question about if it's convenient to just use the model, like yes, it is, but it's a little bit. You've got this sort of fiddly aspect where you've got those two submodels there, and also there are some things where I feel you can go wrong, like this attention mask thing, like this, like that. There's different settings of that. They are a bit fiddly, and it is straightforward to just run the model, with the default case. But if you start poking around like this, like we had to, then it's possible to get it wrong. And I don't think we got it wrong. I think it's working correctly now when we actually use it. But yeah.
Yeah, I have to say this, the zero shot or few shot capability that you get now, as you have described so well today, is really a game changer. I remember I used to work in a project in 2021 where we had like 3,000 different classes, and I tried all kinds of weird, like extreme classification and different kinds of the similarity-based classification approaches, but it didn't really work. And I think now with like GPT-4 or something, it would just work out of the box.
Yeah, I agree with that sentiment. The results are often very good with these models, and they know a lot of stuff, and they give very good results for these kinds of tasks. Obviously, they fall down in certain cases, so it's good to sort of develop a sense for when these models are not going to give good results. But yeah, often they do.
Yeah,
but it was by clip model by 2%. So
yeah, but even the first example that you gave about the car damage, I was working on a case like that as well, like 5 years ago, and I mean, you had to collect the data, train some classifier.
Yeah, it's like, and then you got to curve the damn
now
thing.
You can just, do what you did.
Yeah,
it just.
Yeah, just
much better.
Amazing, game changing, right? Yeah, the possibilities. Yeah.
But anyway, Tom, thanks a lot for a great presentation, and thanks everyone for sticking around and asking questions and things like that. Olivia, I think we need to give you some kind of award for showing up every Friday. But yeah, next week, the next Data Science Friday is next week, and it's with Julia Krantz, and she's going to be talking about AI in fashion and retail. So it should be quite interesting. But yeah, thanks again, everyone, and cheers, Tom. We'll post the replay soon.
Thank you, everyone.
Have a good Friday and a good weekend.
Thank you.
Thank you.
Hello.
Bye-bye.
Thank you. Bye-bye.